This recording is protected by copyright. No part may be reproduced without the prior permission of the University of South Australia.
Hi. L'Hopital's rule. I have a lot of stories to tell about L'Hopital's rule. But what is it for? It is to take limits. Okay? So I'm going to state the rule here. And it says the following. We want to compute. We want to find the limit when x goes to a of f of x divided by g of x. So we want to find the limit of a fraction, okay, when the limit is of a type 0 divided by 0. All right? So that's what you want to do. For example, limit when x goes to 1 of, excuse me, square root of x plus 3 minus 2 divided by x minus 1. So take a look at that. X is going to become 1. What happens in the numerator? In the numerator, you have 1 plus 3, 4. Square root of 4, 2. Take 2, 0. So that's the f. The limit of the numerator is 0. In the denominator, x goes to 1. 1 minus 1, 0. Denominator, 0. Do you, by any chance, remember how we did that in week 1? Yeah. Well, no, it's week 1. When was week 1? Week 1 is 12 weeks ago or something like that. Of course you don't remember. Anyway. But here's how you do it. You can go back to the videos and take a look at what happened in week 1, but here's how we would do it. We used that formula, okay, to get rid of the square root here. I'm not going to reproduce everything, but remember, there was a formula like that. Well, forget that. We have a better way to do it now, and it's L'Hopital's rule. Okay? So here's what L'Hopital's rule says. If this limit here exists, then the two limits you want are the same. The two limits you want. The limit you want and the limit that's on the right here, they're the same. So it is giving you an alternative to finding the limit you want. And what is it saying? It says, look, go in the numerator and take a derivative. Then go in the denominator and take a derivative. Okay? Find the limit of that. And it's going to be equal to the limit you're looking for. So let's go here and see how to apply it. What's the derivative of a numerator? So we want to find the derivative of that. It's the derivative of x plus 3 to the 1/2 minus the derivative of 2, that's 0, so you get 1/2 x plus 3 to the negative 1/2 times 1, which is the derivative of x plus 3. I'm using the chain rule here. So it's 1 divided by root of x plus 3. Oh, divided by 2. There's a 1/2 there. What's the derivative of the denominator? One. Okay? Any questions there? Let's go back to the statement here. What is L'Hopital's rule saying? It's saying now you do the fraction, the quotient between these two derivatives. I'm going to do the quotient of this divided by that. Ah, it became easier, didn't it? This is 1/2 1 on square root of x plus 3 divided by 1. It's this one here. And then I'm going to take the limit when x goes to the value a. A is 1 here. X is going to 1. Does that limit exist? Well, let's see. I'm not dividing by 0. Can I just plug in x equal 1 in here? If I plug in x equal 1, what do you get? 1/4. So yes, the limit does exist, and it's equal to 1/4. 1/4 divided by 1, it's 1/4. Since this limit exists, then it's equal to the one you're looking for. So 1/4. And remember the rule? Remember the old thing? Forget the old thing. L'Hopital's rule has, let's say, it's potentially very useful because it can really simplify a few limits for you. It can really do the trick. Okay? It also could potentially make them harder. But then you don't use it. Okay? Why would it be true? Why would it be true? Because you do this. Look. F of x divided by g of x. Now, it's the same thing as f of x take away f of a. F of a is 0, right? Divided by g of x take away g of a. Because g of a is 0. F of x take away f of a, g of x take away g of a, and now I'm going to divide here and divide here by the same quantity, x minus a. If you do that, you don't change the fraction. Now, the numerator, when x goes to a, when you take a limit when x goes to a, this is f prime of x. And the denominator, that's f prime of x. In fact, this is f prime of a, and that's f prime, g prime of a. Okay? But then you take a limit when x goes to a. It should be the same if the limit exists. Okay? There is a little technical thing there. Let's not bother with the technical thing, because I'm not going to bother with the proof. This is just, this line here is just to convince you that it might be true. Okay. We have good news, too. It's a here. But if you substitute a by, say, infinity, limit when x goes to infinity, the result works. Okay? If the numerator is not going to 0, but it's going to infinity, and the denominator is not going to 0, but it's also going to infinity, so if it's infinity divided by infinity, it also works. So it works in a variety of situations, not only this one. Okay? And the key thing here is that it's useful. So let's see some more examples on how to use it. Okay. Limit when x goes to 0, 1 minus cosine of x divided by x. So let's see. If x is going to 0, the numerator is going to 1 minus cos 0. It's 1 minus 1, because cos 0 is 1. So it's 0 divided by 0. Try to apply L'Hopital. If you don't have L'Hopital, you're going to have to do this in another way. Okay? But try to apply L'Hopital. Limit when x goes to 0 of. What goes in the numerator? What's the derivative of the numerator? Say it. Sine x. The derivative of 1 is 0. The derivative of cosine is negative sine. There's a double negative, so that's sine x. The derivative of the 1. The derivative of the denominator is 1. You're not dividing by 0 now. You were dividing by x, and x was going to 0, so you're going to be dividing by 0. You're not dividing by 0 anymore. So you just plug in x equals 0 in here. Sine of 0 is 0. So this is 0. Oh, come on. It is neat. It is neat. Let's do this other one here. Limit when x goes to 0, 1 minus cosine x divided by x squared. So what is this? I'm going to put equal, even though I don't know whether it's equal yet. Okay? But I'm going to put equal. Oh, it's 0 divided by 0 still. It's a 0 divided by 0 limit here. Equal limit when x goes to 0. The derivative of a numerator is still sine x, as it was before. And the derivative in the denominator is 2x. Take a look at that. X is going to 0. Sine x is going to sine of 0. Sine of 0 is 0. So the numerator is going to 0. The denominator is going to 2x, which is 2 times 0. So it's 0 divided by 0 still. All right? So you can use L'Hopital's rule again. 2 times in a row. Limit when x goes to 0. The derivative of sine x is cosine x. The derivative of 2x is 2. Thank you. You're not dividing by 0 anymore. When you replace x by 0, cosine 0 is 1. 1 divided by 2 is a half. So a half is this limit, it's that limit, it's that limit. Hey, it's working. Okay. Limit when x goes to infinity. Woo! E to the x divided by x. If you don't like e to the x here, you can replace it by 2 to the x, but let's do e to the x. Okay? Now, let's see. When x is going to infinity, the denominator x is going to infinity. So the denominator goes to infinity. The numerator goes to e to the power x, e to the power infinity. That's even more infinite, if you will. Okay? Even more infinite. But it is infinity divided by infinity. So you use L'Hopital's rule. Limit when x goes to infinity of. The denominator's derivative is simple enough. It's just the derivative of x. It's 1. And the derivative of the numerator is also simple enough. It's the derivative of e to the x. It's e to the x. You're not dividing by 0 anymore. So it's the limit when x goes to infinity of e to the x, which is infinite. So this is infinite. You have to always check to see whether you are still doing 0 divided by 0. Because there's going to come a moment, hopefully, where you're not going to be doing 0 divided by 0 anymore. And then you can't keep using L'Hopital. L'Hopital is for 0 on 0 or infinity on infinity. Okay? So if you get to a point like here, and you blindly keep using L'Hopital, where you can't, okay, you're going to get, if you did it again, you would get e to the x in the numerator and 0 in the denominator. Oh, I'm dividing by 0. Can't do. Okay? Can't do. All right? This is a very interesting result here. It's saying that it's saying mathematically what I said in maybe even trying to be funny before, that this is a bigger infinite than that one. If I divide e to the x by x, divide e to the x by x, and take x to be very, very big, this fraction is very, very big. So pick x to be 1,000,000. Okay? I'm going to be dividing by 1,000,000. Whenever you divide by 1,000,000, you could say, oh, this is going to be small because I'm dividing by so much. But look at the numerator. It's e to 1,000,000. It's way bigger than that. I mean, so way, 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 way bigger. And if you take the 1,000,000 and make it 2,000,000, it's going to grow the fraction. Even though the denominator grew, the numerator outpaced it. That's the moral of the story here. Okay? If you could visualize that, okay, take a value for x. Say x is 10. E to the, do you have a calculator there? How much is e to the power 10? E to the power 10.
22,000.
About 22,000. Okay? So it's e to the 10 divided by 10. So this quotient here is like a fraction. Okay? How much more than 10 is e to the 10? Okay? About 2.2 thousand more. Now pick a larger value for x. Pick 100. No, you put it away. No, don't put it away. Bring it out. How about e to the 100? E to the 100 is going to be more than e to the 10, of course.
Yeah, huge.
Huge. Did it blow up the calculator there? Yeah. Try me.
I don't even know. 2.6
Two
1043.
times 10 to the power 43. Now 10 with 43 zeros following it. It's pretty big, pretty big, pretty big. And here you are at 100. But look, honestly, even though 100 is 10 times bigger than 10, in terms of a proportion, it wouldn't even register in here. Okay. Oh yes, my friend. His question is, if it were the other way around, would it be 0? Yeah, if you do the limit when x goes to infinity of x divided by e to the x, it's still an infinity divided by infinity. Okay? Use L'Hopital, which is exactly what you did there. You're going to get the limit when x goes to infinity of 1 divided by e to the x, 1 divided by infinity, 0. Which is another way of saying that the proportion of this guy inside that guy becomes negligible if x is very large. Okay? It's like you are making a lot of money with your investments. But Zuckerberg, anyway. Got that? Now, the interesting thing, so this has a name. It's the growth of the exponent. We're studying how fast the exponential grows. And the exponential grows faster than x. Okay? What about x squared? X squared grows faster than x, right? So what about if you compare the exponential to x squared instead? So let's do that. Bum, 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 bum. Anybody watch the Eurovision yesterday? No? Or the day before? No? So interesting. And a comment like that immediately dates this video, right? Eurovision 2012. Anyway. So let's see what happens if you compare with x squared. And just because you said that, I'm going to reverse the 2. I'm going to do x squared divided by e to the x. Okay? Once more, infinity on infinity. L'Hopital. Oh, was that a smile? Or was that a what?
I was just imagining you saying that's twice as big as infinity.
Yeah, no, it's twice as big as this one here. Okay? It's, 2x, 2 times infinity. It's a funny thing. It's still infinite, right? But no. It is twice as big. And here we're going to do this. We'll pull the 2 out because 2 is a multiplicative constant, so you can bring it out of the limit. And now you have two options. You either do L'Hopital again, or you remember that you did it a moment ago. So this is going to be 2 times 0. 2 times infinity is infinity. 2 times 0 is also 0. There you go. And the conclusion is that, yeah, okay, x squared grows to infinity. But e to the x still grows to infinity faster. Okay? What about x cubed? We're trying to beat e to the x, right? That's what we want. We want to beat e to the x. So we are kind of summoning our minions. X didn't work. X squared didn't work. How about x cubed? What do you think? It's not going to work, because if you do x cubed, you take a derivative, infinity. Here you get 3x squared, e to the x. Oh, 3. It's 3 times better than that one, but that one was 0. 3 times better than 0 is still 0. Okay? X to the 4th, x to the 5th. In fact, the limit when x goes to infinity of x to the power k divided by e to the x is going to be 0 for every k positive that you put in there. So no polynomial that you can think of will ever outpace e to the x for large values of x. For small values of x, of course, you can always be better than e to the x. But that's not what we're talking about here. We're talking about what happens when x goes to infinity, when x is very large and growing. And how would you prove this? Okay. Well, you use L'Hopital once. When you do it once, the k comes out here. The denominator is the same. It's e to the x. The k comes out multiplying, and you drop 1 degree. If you keep doing that, keep dropping 1 degree, you get more guys multiplying, but the degree is dropping. And eventually, the degree drops to one that you've done before. And you already knew it was 0, so it's going to be 0. All right? This is what we mean when we say that something grows exponentially. Sometimes you read the newspaper and say exponential growth. It outpaces any polynomial. Okay? I want to point out to you that an expression like this one can be written like the following. Instead of writing x squared divided by e to the x, you can write, and it's the same, x squared multiplied by e to the minus x. Okay? You cannot use L'Hopital here. This is a product, and L'Hopital is for fractions. You need to turn it into a fraction in order to use L'Hopital. Is that okay? This is not infinity divided by infinity. This is infinity when x goes to infinity, x squared goes to infinity, times 0. Because e to the negative x is closer and closer to 0 if x goes to infinity. Because e to the negative x is 1 divided by e to the x. That's why. Any questions? Okay? All right. A little story. Who was L'Hopital? He was not the man who invented the hospital. No. No. Ha 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 ha. That was such a funny joke. No. He was a French nobleman in the 1600s. And, you know, after calculus was invented, became like the way of science to explain nature, right? And if you have, you know, if you're a nobleman or a noblewoman, oh, many women studied calculus at the time. You would want to know because it was what you would discuss in, you know, evening dinner. Oh, the latest findings of Mr. Newton or something like that. A lot of people started taking tuition, learning calculus. Many of them noblemen, because they could pay. The Bernoullis, who were students of Leibniz, they started teaching. Okay. They are Swiss. And L'Hopital started taking classes with one of the Bernoullis. Okay. Eventually he gave up. He sent Bernoulli a letter saying, well, you know, I decided it's too hard for me. He didn't say that. He said, perhaps my talents lay elsewhere. But I would like you to keep sending me these, you know, letters containing calculus stuff because I find it very interesting. And eventually, L'Hopital published the very, very first calculus book ever. Okay? And if you go to the library or if you have electronic access to it, read it. Get an English translation. Read it. Take a look. Because it's exactly like the book you have in front of you. I don't even know which book you have in front of you. It may be like the one we have, or it may be any calculus book that you pick from the library. They're all a ripoff from from L'Hopital's book. The very first calculus text is exactly like the ones we use these days. But we have more pictures, we have more exercises, but it's the same. Even the order of the topics is kind of the same. Okay? And in that book, there is L'Hopital's rule. First time, very useful rule. And people thought, oh, it was L'Hopital who came up with the rule. But it wasn't. It was Bernoulli. Okay? Because at the beginning of the 20th century, you found a letter from L'Hopital to Bernoulli saying, besides, you know, oh, I decided to give up on this. And send me any results you have, and I'll give you some financial compensation. One of the results was this one. So it should, by all means, be called Bernoulli's rule. But money talks, and people just walk, right? So it is L'Hopital's rule. I think it should be L'Hopital's rule. He paid for it, so there. So we're going to change topic now to a totally different topic. Okay? Perhaps before we do that, one thing that's useful. Okay. So what is the graph of x times e to the negative x, or x divided by e to the x? Okay. When x is 0, this is 0 divided by e to the 0. E to the 0 is 1, so 0 divided by 1 is 0. So you start here. When x becomes more and more positive, this grows. Okay? Becomes positive, so it grows. But eventually, when x becomes very, very large, we know this is going to be becoming 0. So it has to come down and get closer and closer to 0. So this is the graph of x e to the negative x. What about x squared e to the negative x? Well, x squared e to the negative x is going to do almost the same thing, but because x squared is bigger than x, you're going to see something like this. What about x cubed? You're going to be seeing something like this. You get the pattern, right? For small values of x, you do get larger and this fraction can get larger and larger. But eventually, e to the x beats up on the other guy and brings it down to 0. Okay? All right. Your computer or calculator can do a much better job than I can. But I hope this visual, this image will help settle the result in your mind. Okay? When x is larger and larger, this does go to 0. Next topic. And we'll continue after the break into the hour on a new topic. Trigonometric substitutions. A topic that makes everybody's heartbeat go higher. And the deal here is this. You have an integral to do, and you can't find the right substitution. It just isn't there for you. It's not working. For example, the integral of 1 divided by the square root of 1 plus x squared dx. Or, you don't even need the square root there. 1 divided by 1 plus x squared dx. You just can't find the right substitution. Mind you, this one here, the last one I put, and this one as well, if the integrals were this, like this, or like that, then you can find the right substitution. Because what you're seeing here is an x squared and an x. An x squared and an x. So the substitution you would try, and as I said in the tutorial last week, every time you have a fraction, you have to try the substitution that puts the denominator equals y. Right? So the substitution you have to try here is y equals 1 plus x squared. And for that matter, the same substitution on the top one. That will give you that dy is 2x dx in both of them. And so x times dx is dy divided by 2. X times dx is here. X times dx is here. So they are dy divided by 2. One divided by the square root of y. The bottom one, x dx, is dy divided by 2. 1 divided by y. And now you can do them. This one you use the power rule, and this one here you use the logarithm rule. Okay. I'm not going to do the details now because we've done these in the tutorial last week. But you can check that. Now you have the expression in y. You write it back in terms of 1 plus x squared, and you're done. This is the square root of 1 plus x squared plus constant, and that is 1/2 log of 1 plus x squared plus constant. There. Why did it work? It worked because you have the x dx. It's never going to work there. You don't have the x in the numerator that you needed for this to work. So in a situation like that, your options are famous, right? Famous options. Everybody knows what the options are. Find another substitution or cry. Okay? And crying is not such a bad option, okay? But there is a substitution that will work. And I'm going to show it to you right now in these examples here. You may not like it, but here's what you have to do. X is equal to tangent of, now give me a letter you like, theta. Because, you know, we always call angles by theta. It could be tangent of y. Let me call it theta. This is a trigonometric substitution. I'm going to put in a trigonometric function that was not in here before. And in fact, you had absolutely no clue that one was coming. I'll talk about that later, why you should consider it, okay? But that's what I want to do. Now, why do I want to do this one? It turns out that we have this formula here. It just so happens that this formula is the trig formula, and it's lying about there in your bag of formulas. Okay? Like some people have sheds in their house. You go there, you need something, you go to the shed, you open it, and you get the power drill or whatever. Well, you have a bag of formulas too. You never use them until you need them. There's this formula. And if you say that x is tangent of theta, this side here is 1 plus x squared. So take a look at what it does to you here. Take a look here on the board to what it does for you. Or to you, it depends. But this is going to be the integral. 1 divided by the square root. 1 plus x squared is 1 plus tangent squared. And 1 plus tangent squared is secant squared. And what happens here? A square and the square root will cancel each other out. Okay? So this will give me a way to get rid of that square root, this painful square root in here. Getting rid of a square root is great news. What's the price you pay? You have to deal with the trig functions. Nothing comes for free, okay? You can make a choice. I'm going to stay with the square root and never talk about trig functions, but then you cannot do that over there. Not very easily at any rate. Or you can say, okay, I'm going to pay the price. I'm going to use trig functions, get rid of a square root, and live with it. But at least you'll be able to get to the answer. At least. Very well. If you do this in the denominator, by the way, you're going to get the integral 1. Now you don't have a square root, but you still have 1 plus tangent squared. So it's still secant squared. Here you have secant squared. But no square root. You still need to do the rest of the substitution. There is a dx in here and in here. And the dx will turn into something else. If x is tangent of theta, what's dx? Well, what's the derivative of tangent? Thank you. Secant squared. Don't shake my hand because I'm a bit sick. But secant squared. Good. And that's what goes in the box. In both boxes, you get the same thing because you're using the same substitution for both of them. So before we proceed, let's see what's going on here. We had some integrals that the usual substitutions you try do not work on them. I showed you a variation of those integrals in here where a substitution did work before I erased. But it wouldn't work on these. We need a new idea or a little cry. But let's go for the new idea. Okay? The idea here, coming absolutely out of a blue sky, is to substitute x is tangent theta. Now, you do that because you want to take advantage of a trig formula. That trig formula there. And that is the magic reason, okay? The magic reason is there are so many trig formulas about that if you could just find one that helps you, it will help. 1 plus x squared is 1 plus tangent squared, and 1 plus tangent squared is secant squared, and it goes in here. In the in the first integral, the square root and the square will cancel out. In the second, you didn't have a square root, but you can still do this. So let's take a look now at what happens as you proceed, okay? What is the first one here? The top integral, the square root and the square cancel. So there's just a secant in here. And there's a secant squared there. So this is going to become the integral of secant theta d theta. In the denominator, I get even luckier because the secant squared and the secant squared cancel out. This is just the integral of 1 times d theta. Okay? I actually am ready to do the second integral here. What's the integral of 1 times d theta? What is it that is a function of theta? Think of theta as being x, if you will. A function of x that if I take a derivative, I get 1. What gives me derivative 1, guys? X. But don't call it x, call it theta. So this is theta plus constant. No more integrals. You've done it. This one here, oh, more complicated. More complicated. Okay? Integral of secant. Integral of secant. What is it that if I take a derivative, I get secant? Now that's harder, okay? I'm going to freeze this one here and give you the answer later. But this one here, no problem. Done. But it's done, but it's not done quite in the way you want because it's theta. It's not x. What you need to do is bring theta back into x. Take a look. This is the relationship between theta and x. If you give me the value of theta, I can solve for x. Right? But I would like to reverse that. I would like to be able to write theta is equal blah, 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 blah with x in here. Because I have a theta here. So if x is tangent of theta, theta is the inverse tangent of x. Inverse tangent, you cannot do better, okay? You need an inverse trigonometric function. So you come in here and you write tangent inverse of x plus constant. You have to be careful. This symbol here does not mean to the power -1. Easy to get confused. It means the inverse function. Your calculator has a button for it, okay? Or it should have. Let's take a look at your calculator.
Yep.
There it is. The button for tangent, the little thing just above it. In a tan color, in fact. Okay? We do not study trig functions because we absolutely love them. No. Some of us do, of course. Okay? We study trig functions because we absolutely need them. There are some integrals that are important and need to be computed that you only do if you know some trig function because you need to substitute. Worse, after you do the integrals, you will fall into expressions involving the angle theta, not the x that you want. And to solve for x in terms of the angle, or vice versa, you need inverse trig functions. We don't study inverse trig functions out of an absolute love of inverse trig functions. We do it because they just happen. Okay? So when we come back, we're going to be a bit more systematic. I told you why, and the examples are here. We're going to be a bit more systematic. We're going to take a look at integrals that will give you sines and cosines and stuff like that, and we'll take it from there. So take 5.